Good morning, good afternoon, good evening, everyone. Welcome to Lecture 2. It depends what time you're watching this lecture, but I know I didn't post something for a while, but here it is. In this lecture, we're going to talk about analysis of algorithms and dot dot dot. Well, that depends on how far and how fast we get through this material because it is important. It's still, it's so important that I still deal with it up until this day. And algorithm and the runtime for algorithm is something I test on the people that I hire into my team in the real world. So and many big companies do it. Amazon, like in my case, Microsoft, Google, all of these companies, they'll test you for the runtimes of the algorithm. So without further ado, let's jump right into it. Now, if you're gonna read the book, like it's chapter 4 from C++ book, it starts off by, analysis of algorithm. All it is, and what we're trying to do is find out how good, how bad, how fast, how slow the solution that you gave, like algorithm that we talked about in the last lecture, is going to do. All right, how fast is your solution? How fast is your algorithm? That's the bottom line. Now, the book talks about experimental studies, primitive operation, some other types of analysis, but I'm just gonna get to the meat of it. What we use today. You don't really have to worry about anything else for now. Well, before I go any further, there is a mention of the seven functions: constant, logarithm, linear, n log n, quadratic. Not gonna get into it. It's not really all that important in my opinion. As long as you understand the runtime of Big O, you should be okay. Well, Big O notation. And as I said, we want to find out the speed of your algorithm. Um, and why do we even care? Now let's think of this scenario. If you have to iterate through an array to go through 100 items one at a time, it's okay. How about 1,000? Okay, 2,000, 10,000, a million is getting big. 10 million, 100 million. It does have an impact because your algorithm, if you have a linear algorithm, let's say for example, a linear algorithm, an example of that would be it takes me 1 minute to read one page. 100 pages, 100 minute, 1,000 pages, 1,000 minutes, so on and so forth. So as this number n, as the number of pages increases, um, the time increases as well. And big O is just a way to represent how fast or how slow your algorithm is. Now, one thing to keep in mind is it doesn't necessarily mean that it's in milliseconds, seconds, hour, minutes, whatever. It's in a different format, and we're gonna talk about those formats right here. So O of one, okay, is is the fastest and constant time. A lot of the operations are constant math operations. If you access an array, you get a million items in the array. It doesn't matter. If you say A at 100, A at a million, that index, it's going to get it for you right away, very fast. You don't have to go through the whole entire list to get to the millionth item. You can use it via index, accessing a hash via the key. Pushing or popping from the stack is also O of 1, right? Because you can push it immediately. It doesn't matter the size of the stack. You're pushing it onto the stack, and stack is last in, first out. Pushing something onto the stack, you do it right away. Popping, retrieving it, the last item that you put in comes out. So it's O of 1. um, O of n. Now remember the book reading example that I was talking about? How it changes as the number n grows. So O of n is just linear, okay? If it's one value, it's one. It's 100 value, it's 100 million, it's a million. So it's gonna grow based on that number n. Now, if you look at this example, you've got a array of 4 elements, and then you've got an array of thousands of elements. Now, if you print all the values, if you've got thousands of elements, you're going to have to go through each element one at a time. Think of how slow it is. I mean, as that number grows, this thing is going to get slower and slower. So imagine you've got some sort of an API, some sort of a logic that goes through all the items in the collection, like a bookstore. Amazon started as a bookstore, right? Now it's got millions of books that it can sell from. If if it grew at that rate and their logarithm algorithm was O of n, it would be slowing down for every book that they've added. And if you want to search through the library, it's going to get even slower. So O of n isn't that great. O of n squared, what do you think? Gets even worse, right? Means that the calculation runs in quadratic time. Square square of n. Many of the, and you're going to get to see this at some point, bubble sort, insertion sort, selection sort, these sorts of sorting algorithm, they take n squared because there are two loops that they go through. Because in the previous example, it was O of n, right? And then now it's n squared. The two loops that I'm talking about. Look at this. You've got collections here. If you get iterate, if you get two loops, n just gets squared. So it's getting worse. Um, then there is the O log of n. Now O log of n is pretty decent. Means the running time grows based on the number n, but it grows very slowly. Log of n. Think of it as looking at retrieval from a dictionary. If the word starts from N, you're gonna open up your dictionary. Let's say you open up at L. Everything before L you're gonna skip, and then you're gonna go, and you're gonna keep halving it every time. You're gonna get closer and closer to the destination fairly quickly. You don't have to go through all the pages, but you're gonna open up in the middle or 2/3 or towards the end, depending on where the letter is. So O log of n is pretty good. You're getting good runtime for this. But one thing to keep in mind is there's also n log n, which is confused with log of n. Um, Sorting algorithms that utilize a divide and conquer strategy are linear rhythmic. It's a mouthful, right? Such as merge sort and heap sort. Um, So, what do you think? N log n is better or log n? Log n is better, right? Because you don't have that preceding n in there. Um, you can use this as an example. I found this online, and I thought it was a great way of representing the runtime. You see that? How bad O of n factorial, O of n to the power 2. Now, when we get to the log, n log n is getting better, right? The best is log n or O of 1. Constant number. Those are the fastest ones. I wish I had this cheat sheet when I was studying. It wasn't my favorite topic, the log timings, the runtime for an algorithm. But, later on I learned it the hard way. So, look at enough examples. Make sure you familiarize yourself with this. Um, and you're comfortable enough with it right now so you don't have to struggle in the future. Okay, um, so the next chapter, chapter 5, is about, the NQ, DQ, stacks, queues, which is a very important and very useful data structure. But the base of, let's say, stack is the vector. Vector is a very important data structure that you can study about right now, and it'll come in handy. And it's something you're going to use over and over and over again. But I still, up till this day, until this day, I use it. So, without further ado, let's talk about vectors. It's part of the standard template library. Standard template library is something that's available for you to use. It's got many algorithms, many storage mechanisms in there, and one of them is a vector. A vector, think of it in a very simplistic way, is array. It's as simple as that. Um, the first one mentions copying of a vector. Okay, I'll walk you through those examples. But one thing to keep in mind is a vector has this concept of iterators. Iterators are similar to index. The iterator, first one is the iterator specifying the beginning of the range. The last is the last iterator specifying the end of the range. Um, and then, so like I said, think of it as index. So first and last, you're going to keep using it. Let me show you example without it before it comes to me. So the things to keep in mind is you're going to include the library algorithm. Okay, you're going to use vector. Okay, and look at this declaration. So vector, like I said, it's an array, similar to an array. If you really want to be technical, it's a dynamically sized array. Every time you reach the size of the array, it's going to double it up for you in the background. So in here, I've got an array of ints, vector of ints, okay? And I'm going to try to sort them. Well, I said copy first, right? Let's do the copy one. And then we'll come to sort. Let's copy this. So my vector is called source. Begin, right, is the starting. End is the end of the vector. So I copy from the beginning till the end, and then I copy it into the secondary vector. Okay, now let's see what happens. So destination now has source copied into it. Straight enough, right? Understandable enough. Hopefully this is straightforward for you. So just remember the concept of iterators and think of vectors as a dynamically sized array. And then you, as part of the vector and the algorithm library, you get it handed to you. You know, in C, people don't have this luxury, so they have to declare an array, resize it, etc. But C++ comes with all these perks, and this is just one of them. So copy is one method. The next method is sorting. So you've got a integer vector once again, right? So it's unsorted, 4, 2, 3, 1, 5, and then you want to sort the whole thing. I mean, one thing that comes to your mind is maybe you could do n minus 1, n minus 2, n minus 3, 4, 5, whatever. But in this case, sort, I'm going to sort the whole thing. And after sorting it, you get this. I'm going to run it again. 1, 2, 3, 4, 5. So once again, the work of sorting it is done in the background for you. It makes your life a whole lot easier. Next up is, what do we want to talk about? Move. Okay? As the word suggests, you're moving the vector content. So now see what happens. Without giving the definition, let me walk you through this. So you've got a source, apple, banana, and cherry. You get an array of string, vector of strings. And then you've got a destination, 3, right? 3 items can be held in that destination vector. So we say before move, the source was this, okay, and then we output the string for the source and destination, and then we use the move operation. Takes a beginning and the end, destination that beginning. So what's going to happen? And then we output source and destination after that. Before move apple, banana, cherry, you saw source had contents, destination was empty. After move, destination had content um, and source was empty. So we literally move the contents from one place to another. This is not a copy. This is moving of content. And in the background, what happens is you're making the destination point to the memory address for the source. Okay. Now, next example up is swapping. Swapping of the vectors. Right? So let's walk through this. We've got two vectors, 1, 2, 3, 4, 5, 6. Before the swap, vector 1 is this, vector 2 is this. Now if I say swap, vec 1, vec 2, what happens? Just a little slow. It should swap the two vectors for you, that's what it's going to do. But these are just some of the examples. These are not all the methods in the vector class. There are more. You can look them up. But highly useful class. I mean, like I said, we cannot move to stacks and queues without you knowing about these, knowing about the vectors. Okay, so now let me go ahead and get into stacks and queues. Stack is defined for you already. Okay, it's part of the library. You get a library, like to say, includes stack for you to use stack in your program. And the key elements. Well, before I mention the key element, stack is based on the on the principle of last in, first out. The books in the past always tend to use this example of a stack of plates, right? When you put a plate, um, the first one that you put is at the very bottom, right? You keep stacking them on top of each other. And the first one that gets out is from the top. So the one that you pull out is the one that was the last one in. So that's the principle of stack. And then the methods included for you to use are empty, size, top, push, and pop. Okay, push and pop are the main ones. Push is inserting an element, pop is deleting an element or taking one out. Size will tell you the size of the stack. Top will give you the topmost element. And then the runtimes will also mention. Empty will actually tell you if the stack is empty or not. It's all one. The fastest algorithm size, it's all one, right? Because it probably has a counter in the background, and that's how it knows what the current size is. It gives you back right away. Top, you get the top element right away. All one. Push, all one. Pop, all one. So all of these stack operations are really fast, all one, constant. Doesn't matter the size of the stack. The runtime still remain the same. Let me go ahead and jump into some examples. In here, so you would include stack, right? Like I said, you would include the library stack. So you get all the, you get stack and all the elements that come with it. And the way you declare it is, surprise, surprise, is how you declare a vector, right? So a stack of integer called stack, and I push 21, 22, 24, 25. Now, the one at the top, what do you think is going to be? The last one you pushed in was 25, so it should be at the top. And then I push number. I push 0 after 25. Then I pop 3 elements. And then while stack is not empty, I output what's at the top, and then I keep deleting elements. Right, so I pop elements already. So I push them, I pop them, and then at the end I retrieve, I see what was at the top, and I pop once, and the stack is empty, right? That's because of these 3 pops right there. Because you essentially put in 1, 2, 3, 4, 5 elements in there, but at the end you're seeing only 2. That's because you pop in between. Okay, so that's a simple example. to illustrate push and pop. Let's run this one. What is this doing? False. I have a stack and I push one, just one element in there. And this is to illustrate the empty method, right? So empty will tell you if it's empty or not. In this case, there was something in there. What if I didn't have this in there? What do you think is going to happen? True. There's nothing in there. Simple as that. So in this, I keep adding to the sum, and I keep popping. So I have, so I have a stack, and then, now look here. I didn't really tell the size of the stack to begin with, right? It's dynamic. You keep, you keep adding to it very easily. So I push one, I push eight, I push three, I push six, I push two, and then while it's not empty, sum is equal to sum plus whatever is at the top, and then you pop it. So what should happen is at the end it should sum up all the numbers. 20, right? So 20 is the number, 6 plus 2 is 8, plus 3 is 11, plus 8 plus 1 is 20. So that's where you get the number 20 from. Continuing on. For now we're going to go ahead and talk about the final section for this chapter, for this lecture, I should say, is cues. So you might have already guessed is if you want to use Q, you have to include the library Q. And these are the methods that come with it. Empty, as the word suggests, it's going to tell you if the Q is empty or not. Size, it's going to tell you the size of the Q. Swap, it's going to swap the contents of the two Qs. The size can be different, but the type of the elements that are in the Q should be the same. So if it's an int Q, you're swapping it with another int Q. So you cannot do int and a float. So keep that in mind. Give it a try. See what happens. Does the compiler complain or what happens? In place, insert a new element into the queue. Front, it's a reference to the first element. Back, the last element, right? So push is going to add an element, pop's going to delete an element. But one thing to keep in mind is queue, as the word suggests, queue, it's like a line that you form. So the first person that comes in is going to be the first one out. So he's all the way in the front. Next one's going to go behind him, and then behind him, and behind him, all the way to the very last. And when it's time to go into the store or wherever you're trying to go, guess who the first person is going to be in the store, right? He'd be the first one that came in, and the last one that came in is all the way at the end. Let's look at the runtime. So just like the stack, the runtimes are very fast. They're all O1. So it's an instant run that you get. There's nothing faster than O1. Okay, now let's jump into some examples of Q right here. Close this window. Close. Oh no. Okay. So first, let me illustrate push and pop. So I included the library Q, okay, and then I have a queue of ints, and I'm going to push 5, 13, 0, 9, and 4 in it. And then as long as it's not empty, I'm going to output the queue. So see what comes up. 5 was the first one in, right? And then that was the first one in, first one out. Simple as that. Next up is the standard template library representation of Q. So show Q, all it does is it takes in the Q, and as long as it's not empty, it outputs T, and then pops it. Um, Not T, G dot front. It outputs whatever is at the front of the queue. Slash T is just for the tabular format. So the output is clean. So here I push in three elements first, right? 10, 20, 30, and then I call show. Show is gonna output, right? It's gonna output the front, then pop, output the front, pop, so on and so forth. And then here it's gonna output the size and what's at the front and what's at the back. And I'm gonna pop it and then show it again. So now let's see what happens. Okay. So the queue is initially 10, 20, 30. And then the size is 3 because I've got 3 elements in it. The front, right, the first one is 10. The back, the last one, is 30. And then I pop it, I only have 20 and 30 left in there, right, because I popped the first element. Another example, swapping. So I've got 2 queues, both are int, right? And I'm not going to try to swap um, float to an int or vice versa or anything of that nature. So I pushed in 3 elements in Q1 and then 3 elements in Q2. First one has 1, 2, 3. Second one has 4, 5, and 6. And then I print Q2. And then I say Q1 swap Q2, right? So I'm swapping the two. And then after I swap it, I print the Q1 and Q2, right? And then I output if Q1 is empty. So let's go ahead and run this. So first Q is 1, 2, 3. Second is 4, 5, 6. After I swapped it, it's the other way around, right? The first one becomes 4, 5, 6, and then the second one becomes 1, 2, and 3. And then I check was Q1 after swapping empty. It wasn't empty because we swapped it. Now obviously vector-based implementation in the background. It's swapping these elements for you. And once again, you can take it for granted. These methods are built in, and then you get along with the C++ compiler and the library. You get it with the library, I should say. The compiler will compile it for you. Okay, so far with me? And now if you've seen the stack, Q is going to be similar. So here, I am going to output the front of the queue and then remove the front. I'm going to keep doing this. So I pushed 1, 2, 3, 4, 5 elements in there. And while the queue is not empty, I will output whatever is at the front, then throw it out, output it again. So what should happen theoretically is you should see all the elements in the queue. Right? 1, 2, 3, 4, 5. So as and when you're popping it out, you output the front and then pop it. Okay, so now moving on to the next example. Excuse me, my throat is still itchy. So this example is traversing on copy queue until it becomes an empty queue. See what happens here. I created a queue and then I pushed elements to it. Then I have a copy queue. So while copy queue is not empty, I say copy queue dot front. What do you think is going to happen? Let's run it. Elements of the queue are 1, 2, 3, 4, 5. Because, and this is a different way that when I created a copy queue, I didn't really swap the elements or do anything. I just initialized the copy queue to the first queue. This queue right here. Okay, so now the last example is iterating through the queue, through the DQ. Maybe I should hold on to this example till the next one because I didn't talk much about DQ yet. Um, yeah. So I think that'll be it for this lecture. I'll see you guys in the next lecture.